In 1908, Earth had a visitor from outer space. Investigating scientists found immense devastation, caused not by aliens, but by a remnant of our early solar system. Today we know that billions of such objects traverse our solar system and occasionally make their way to Earth.
In modern times, over the last few centuries especially, it was difficult to convince the scientific establishment that rocks fall out of the sky, no matter what the ancients had to say about them. The picture really wasn't transformed until 1803, when a fall of meteorites occurred in l'Aigle, France, and was witnessed by a large number of people who could pick up the meteorites afterward.
The French Academy sent some investigators out and concluded, by golly, they did fall out of the sky, and these rocks really did come from up above. And finally, scientists at that time then began to realize we are receiving rock samples from space.
Even then, you can sense the resistance to this kind of a notion. In the words of Thomas Jefferson, a president of the United States, who said that he would rather believe a pair of Yankee scientists would lie than that rocks could fall out of heaven. Well, as it turns out, rocks really do fall out of heaven, and it takes a couple of things to be sure that that's so. First, you actually have to see, at least once, one of these things fall out of the sky and be able to pick it up. But that's not enough. Once you pick it up, from its structure and its composition, you have to be able to show that it is not of this Earth.
You must remember, when you look up at the sky and you see a shooting star, you're looking at a very tiny object, maybe the size of a grain of sand zipping through the air. The light effect it makes passing through the atmosphere is called a meteor, and if it survives and lands on the Earth as a tangible object that you can pick up and study, then it's a meteorite. So you can imagine if a big meteorite comes in, then it's quite a awesome event. If we get a specimen we think is a meteorite, the first thing we do is check it to make sure it has nickel in it, because that's our first clue. Of course, if you're used to looking at meteorites, you also can tell by looking at them whether you have one or not. And if you've seen a lot in museums, this gives you clues as well.
We classify meteorites into such categories as stony, iron, and carbonaceous. Each brings us different clues about the nature and evolution of our solar system.
The stony ones are almost entirely silicate material, the type of material that sand is made of. And these comprise the vast majority of the meteorites that are found on Earth. The other type is the irons, and they're, of course, made up of iron, nickel, cobalt, but they represent a very small percentage of those objects found on the Earth's surface.
There are other types as well. We find meteorites on the Earth, for example, that are very rich in carbon compounds, and not just graphite and the simple ones, the simple carbon compounds, but complex organic materials.
The real main reason we study meteorites is that they're the oldest samples we have available for study. In other words, if you run a radioactive date on them, you can date the meteorite very precisely. They're mostly 4.5 billion years old. Essentially, all of the meteorites were formed at the beginning of the solar system.
We can study their chemical composition and determine the chemical mix from which the solar system formed 4.5 billion years ago. The trick is, of course, to relate this meteorite that we have in our hand and study in the laboratory to its origin. Where did it come from in the solar system? Where did that particular object originate?
Astronomers realized before the 19th century that there was a kind of an arithmetic progression of the distances of the planets from the sun. And when the planet Uranus was discovered, its orbit seemed to fit the pattern. And so they took it more seriously and began to ask whether or not there really might be a planet between Mars and Jupiter where this pattern seemed to suggest there ought to be one. The astronomers went looking for it, and the astronomer Piazzi found an object on the 1st of January, 1801, more or less in that general part of the solar system. And they found another one in 1802, and a third one in 1804, and a fourth in 1807, and by 1891 they had found 321 of them, and it didn't stop there. We now know that there are at least tens of thousands of these objects, the largest being about 500 miles in diameter, and they range all the way down to as small as you want to talk about.
They're very interesting in the sense that apparently Jupiter's gravitational field kept material in that part of the solar system from forming a large planetary body. So apparently, anytime material started to come together, Jupiter would tear it apart.
In recent years, we have begun to explore asteroids using spacecraft. The Galileo spacecraft, on its way out to the planet Jupiter, flew past two asteroids, Gaspra and Ida, in the early 1990s, and took the first close-up pictures of asteroids and made some other measurements of asteroids. One thing that we learned from the Galileo studies of Gaspra and Ida were that the crater populations made by still smaller asteroids were very different on the two objects. And they reveal that Gaspra is much younger than Ida. Ida has been around 10 times as long, being exposed to a rain of projectiles from space.
Through spacecraft and Earth-based observations, we've identified different types of asteroids, possible remnants of the early solar system. Most of these fall into one of three major groups: S, M, and C.
These letters that we use generally indicate what we think they're made of. S, for example, is the abbreviation we use for those comprised primarily of silicate rocks. And many of those, by the way, are rocks that are very similar to the rocks coming out of volcanoes here on our planet. The M-type asteroids we think are primarily metal. And by metal, I mean a combination of iron with a little bit of nickel and a few other metals mixed in. So these we think are primarily metallic objects. The C-type asteroids, we call them C because that reminds us of carbon, tend to be very dark, that is low in reflectivity, and so they are very much big black rocks in space.
Learning the composition of asteroids led to some exciting conclusions about the meteorites we find on Earth.
We think we have at least the rough answers that the metal, the nickel-iron meteorites that we have in our museum match the M for metal, asteroids. We have the general rocky, sort of your average routine run-of-the-mill rocky types, which are very common, rocky meteorites, which match up with the S for stony asteroids. And then these carbonaceous black ones, which match up with the class C. So asteroids are wonderful. All the time, during the 4.5 billion years of solar system history, fragments from the asteroid belt have slowly, few at a time, been fed into the inner solar system where the Earth is, intersect the Earth's orbit, crash onto the Earth, fall out of the sky. Presto, we have samples of the insides of asteroids falling on the Earth, and we go around and collect them.
These celestial fragments tell us much about the composition, structure, and history of the solar system. Yet, from far beyond the realm of the asteroids, even more intriguing tales come from the icy debris that sometimes journeys our way.
Comets were bad news. They were bad news either because they caused catastrophe or they brought the message of catastrophe on the way. Now, obviously, comets don't really do that, and so it's a fair question to ask, why would a comet have this association with disaster? Well, the answer is really, again, pretty simple. Comets seem to come out of nowhere and go off to nowhere again, so they didn't seem to obey the rules, and they were, therefore, emissaries of chaos in an otherwise orderly universe.
People thought of comets as portents of doom and catastrophe. They expected the appearance of a comet to portend the death of a king or some catastrophe to the army or the nation. And in fact, at least one comet has been very, very good news for the history of science, and that's the comet that we now know as Halley's Comet. Edmund Halley was a friend to Isaac Newton, and he began to use Isaac Newton's theory of gravity and motion to analyze old observations of comets, and he realized that one comet that had been seen many times before was actually the same comet following an orbit that brought it back around the sun every 75 years or so.
It had come in 1682, so he predicted its return in 1758. He was somewhat ridiculed for setting the date so safely beyond his own lifetime, but in due time, the comet reappeared, and it was the French who named it Halley's Comet, and it's been coming back rather systematically ever since.
Upon its last return in 1986, we greeted Comet Halley with an armada of spacecraft designed to chip away at the secrets of its primordial ice.
We saw that Halley's Comet's nucleus is an irregularly shaped object which is very dark. That is, it has a black surface, and that information itself may be telling us something interesting about what it's made of. We know that the interior part is made largely of ice, but a third of the mass of Halley's Comet is organic material, which most scientists agree is material formed originally in the interstellar medium.
Astronomers find comets by going to the telescope and taking large photographic plates that cover fairly large areas of the sky with their telescopes. They then take those plates back to their office and look through search the plate essentially for something that moves or for something that's has a little more fuzziness around it, has a tail, a coma, something like that.
But as a comet in its orbit comes closer to the sun, it begins to warm up. And as it does, the ices begin to slowly evaporate, much as do ice cubes in a frost-free refrigerator. The ices slowly sublime and evaporate away. They produce a halo or a coma around the solid nucleus, and the stream of particles blowing outward from the sun, which we call the solar wind, causes this halo or coma of the comet to be stretched out in a long tail, which is directed exactly opposite the direction to the sun. Then, as the comet continues on its orbit, having passed the sun, goes back out toward the more distant regions of the solar system, cools off, and the ices no longer evaporate, and we return at large distance from the sun to just an icy, dirty ball of the comet's nucleus.
Many scientists speculate that the journey of most comets begins far beyond the last planet, in a spherical cloud, a third of the way to the nearest star.
All of the comets believed to exist in the solar system could have originated in the vicinity of the outer planets, Uranus and Neptune. And the Uranus and Neptune, these giant planets, can act as slingshots. And as the comets pass close to these outer planets, they're flung out very far.
But once in a while, a nearby star or molecular cloud will perturb their leisurely motion and send them in any direction, and some fraction of these might be directed toward the inner solar system where we'd have a chance to see them.
We had long observed the results of space debris slamming into planets and moons, yet had never witnessed an actual impact. Then, in 1994, astronomers observed the comet hurtling toward the swirling atmosphere of Jupiter.
The comet was discovered in March of 1993 by Gene and Carolyn Shoemaker and David Levy. And they discovered an object that was very near Jupiter that was actually composed of a series of small comets, all in a line. And for that reason, it became known as pearls on a string.
Because we are a conservative lot by nature, we were saying that the changes in the atmosphere of Jupiter would be very subtle. You would need fairly large telescopes to observe anything. And so when the impacts started occurring, when fragment A, the first one in, struck and formed this enormous black plume that spread out like a fountain over the surface of Jupiter, much larger than the Earth itself, this plume. It was just pandemonium in the astronomical community. People were cheering, shouting, they were breaking open champagne at the Hubble Space Telescope Institute.
We had a great sense of anticipation that the later fragments, which we knew were bigger, would be even larger and have larger plumes.
What happens is, as this piece of material comes down into the atmosphere of Jupiter, the pressure on the front side builds up, and it's much larger than the pressure on the back side. And so after a while, the fragment actually pancakes until the pressure becomes so large that it detonates explosively and sends material back up the well that it just dug in the atmosphere of Jupiter.
As the impact sites rotated into view, we could see large dark spots, scars really, on the planet in the visible wavelengths. These areas are about the size of the Earth, or twice the size of the Earth.
Two of the surprises that came out of the Shoemaker-Levy 9 impact results were that sulfur was identified and water wasn't. If comets are made up of water, and these fragments were thought to have punched down into the atmosphere to the water layer of Jupiter and blown water up into the atmosphere, why didn't we see it? Well, maybe the water layer is lower, maybe there isn't a water layer. And the other problem is, if this thing is a comet, it's mostly water ice, why don't we see water from the comet itself, even if the comet didn't get down to the water layer in Jupiter?
Scientists speculate the comet may have lost most of its water ice through eons of traveling in space. Still, it produced planetary-sized explosions. And while these collisions took place on an outer planet, many other cosmic projectiles are hurtling through the inner solar system, dangerously close to home.
What are the chances we'll be hit by an asteroid or a comet? If you take the long view, the chances are exactly 100%. We will get hit. It's happened before. On the short term, this month, this week, our lifetimes, we probably won't collide with an asteroid or a comet. But on the long term, over the history of human civilization, it has to happen eventually.
Once in a while in the asteroidal belt, these asteroids run into each other. And when this happens, they get knocked out of their regular orbits and get into perturbed orbits, which may cross the Earth's and Mars and Venus's trajectory around the sun.
Those asteroids are in very dangerous traffic patterns because they're eventually going to run into a planet. And that's why when we look at planets, we see big craters on them. There's debris, there's traffic all through our solar system.
The asteroids across the orbit of the Earth are fairly small by asteroidal standards. The largest one is about 10 kilometers across. But if something 10 kilometers across or even 1 kilometer across were to strike the Earth, the results could be devastating. And there are hundreds of known objects in Earth-approaching orbits.
The frequency of near misses is at this point based on very little data. But those data do suggest a rather alarming picture. If you consider an asteroid half a kilometer in diameter, the estimates now are that you get one of those passing within the Earth-Moon distance once every 18 months. So if you imagine a dartboard, if you like, with a bullseye, and the bullseye is the Earth, and the dartboard is the orbit of the Moon, then every 18 months, somewhere on through that dartboard, an asteroid about 500 meters in diameter, about half the size of the ones we are afraid would wipe out civilization, passes through this dartboard.
About once a year, there is an asteroid or comet impact on the Earth's atmosphere with the force of the Hiroshima atomic bomb going off. This is an object maybe the size of a room that strikes with that kind of force. Fortunately, that's high in the atmosphere and does no damage. About once a century, there's a blast, perhaps 10 or 20 megatons of energy, and that's due to something maybe 50 yards, 50 meters across.
There is evidence, of course, that the Earth has been bombarded. Most of this evidence has been erased, but there are great scars on the Earth that are the result of meteorites. One of the best known ones is the small crater in Arizona, which is a little less than a mile in diameter. But the Sudbury Basin, for example, in Ontario in Canada, is over 100 miles in diameter. Related to this is the Great Tunguska event that hit Siberia early in this century. In that case, it was not an asteroidal object, but was a cometary body.
The icy comet that exploded in 1908 over the Tunguska region of Siberia leveled over 2,000 kilometers of forest, destroying virtually all life in its wake. Yet, this immense explosion is dwarfed by a much earlier and far more devastating impact known as the KT boundary event.
Mass extinctions that have occurred many times, there are about 9 serious extinctions, all appear to be related to very sudden events. And the famous KT boundary event, which involved the extinction of the dinosaurs, now looks almost certainly to have been an impact event, a very large asteroid about 10 kilometers in diameter that struck 65 million years ago.
People have spent a lot of time looking for the scar of this impact. And the best guess at this time is a large crater in the Yucatan Peninsula of Mexico. The main idea is not that the meteorite hit and killed the dinosaur. It's just that it threw so much dust into the atmosphere and produced such a shock that it insulated the surface of the Earth from the sun. The plants didn't grow. The dinosaurs were very specialized, and they were stressed so badly they died out. The other interesting fact is that many, many other organisms, maybe an estimate of 20 or 30% of the living species on the Earth disappeared at the same time.
We are descended from mammals that made it through this terrible event 65 million years ago. So asteroids and comets striking the Earth have changed the course of evolution of life on our planet by upsetting the relatively delicate environmental balance.
Now ask yourself what would have happened if the asteroid had missed. If it had arrived an hour later or an hour earlier, it would have missed. Then we wouldn't be here. The dinosaurs would not have been wiped out, and mammals would not have been able to have that chance to rise to ascendancy.
It's a radical new idea in terms of biological evolution and geology that the emergence of mammals could have something to do with random impacts, random asteroids falling out of the sky and hitting the Earth.
Indeed, if such a massive object were to strike the Earth today, what would happen to life on our planet?
If an asteroid about 1 kilometer in diameter was to strike the Earth now, it would take approximately 1 second to go through the atmosphere. In passing through the atmosphere, it produces a shock wave. There is so much energy in that shock wave that it raises the temperature of the air to thousands of degrees. So everything that's within what's called the line of sight to the asteroid going through the atmosphere would catch fire immediately. Everything would burn.
It really doesn't make any difference if an object a mile in diameter hits the land or the ocean, if you think about it. The ocean is not going to cushion the blow. That meteoroid will blow the water away from it, perhaps forming a tremendous tidal wave, of course, that will wash debris up over the land.
The computer simulations of what might have happened 65 million years ago is that a wave approximately 5 kilometers high, 30,000 feet high, was created. That wave must have washed over a good part of the United States. The computer simulations suggest that even Kansas City would have felt the water lapping at their shores, so to speak, from an impact in the Caribbean.
If the object is very large, then it can blow material both from the meteorite and from the Earth up into the stratosphere. And that dust may stay up there for 10 or 20 years, and then rain down all over the surface of the Earth.
The impact itself would annihilate the asteroid and produce an incredible amount of dust, which quickly encircles the Earth and cuts out sunlight to produce what's now called impact winter, which may last 6 months to a few years. It is during that winter that the world's food supplies would essentially come to a screeching halt, because there would be no summer and the crops would simply not ripen.
It would also destroy the ozone layer around the world and probably change the chemistry of the oceans, acid rain worldwide, and perhaps threaten civilization as we know it, produce another mass extinction of species of life on this planet.
Asteroid impacts pose probably the greatest danger to the human species, far exceeding anything that we can imagine that we ourselves would do to destroy the Earth. The current thinking is that an asteroid about 1 kilometer in diameter, if that was to strike, it would essentially wipe out civilization, not by killing everybody, but by destroying our lives, what we're so used to, which is adequate food supplies, destroying that so totally that those people that didn't actually get killed in the impact would die as a result of the catastrophe, the chaos that would follow. I liken the asteroid danger something to a sleepwalker who is wandering into the middle of a freeway somehow and then wakes up and realizes that he's in tremendous danger. What do? Well, the first thing is you look at which cars are coming towards you and you step out of the way. I see the human race as having been sleepwalkers, and suddenly the astronomers have discovered that we live in a swarm of asteroids, and now we better see where they are, which ones are coming towards us, but we can't step out of the way.
If an Earth-approaching asteroid were found heading toward Earth so that it would crash in the next week or the next year, there's not a lot that we could do to keep it from happening, although we could perhaps evacuate people from ground zero, we could store up food supplies and make some advanced preparations. But if we had a warning time of several years, which is actually most likely, it's within our technological capability to send a rocket up to the asteroid and blast a bomb in its vicinity that would just give it a little bit of a changed direction so that years or decades later it would miss the Earth rather than hit the Earth.
But the first thing is to find where these asteroids are. And we may be unlucky, maybe we'll see one and we won't have time to do anything. But I think it's imperative that we do something.